Hello everyone, myself Noel Manna, Assistant Professor of Electrical Engineering Department, Huldia Institute of Technology. So today I am going to discuss resonant circuit. So first of all, resonant circuit contain resistor, inductor and capacitor, which are the basic element of electric circuit. Now if we see the frequency response of any resonant circuit, then it looks like this. So here, as we can see, with the increase in frequency, if we see the voltage or current characteristics, then it increases, and at a particular frequency it gets to its maximum value, and then it reduces to a very lower value again. So here what we can see is that at a particular frequency, the characteristics get to its maximum value, and as we go at the far end from that particular frequency, then the magnitude of voltage current that gets reduced to a very lower value. So what will happen is that if we select a range of which is far away from the particular this frequency FR, then the power that is or the energy that is there with this particular frequency signal, that is very less. So that is not that much useful. So therefore, for resonant circuit, by resonant circuit we set a certain range of frequencies, or we tuned the circuit in such a way that it takes a certain range of frequency in which the voltage and current magnitude has some considerable amount of power or energy that is stored and that we can transfer. So this way we use the resonant circuit. Now there are two type of resonance. One is series resonance and this is called parallel resonance. So if we see the series resonance, the RLC elements are in series, and for the parallel resonance, these components are in parallel. And here for the series resonance, we can see that the characteristics over here, the frequency response curve, that is plotted against the current through the circuit, that is plotted against the frequency, whereas for the parallel resonance, the frequency curve that is plotted between voltage across the elements with the frequency. Now, if we see that series resonance circuit and parallel resonance circuit, for all the cases, the resonance, whenever we are talking about, then we will see that at resonating condition, the power that is stored in the inductor and power that is stored in the capacitor, they changes their power from one cycle they store in the inductor, and on the other side cycle that power goes to the capacitor and being stored, whereas there are some amount of power that is being consumed by the resistor, and this is shown in the graph. So here we can see that whatever may be the circuit, whether it is series or parallel, the power in one cycle, the power is stored in the inductor that is being delivered to the capacitor, and in the next cycle, the power is being again coming to the and storing into the inductor. And there is some resistance which dissipates some amount of power, which is an average power that has been drawn over here. So you can see from the equation what is the total impedance from the supply end, what is the total impedance, that is over here R plus J XL minus XC. This is the total impedance, whereas for the parallel circuit it is better to represent the total impedance, but in terms of this admittance it is better to represent. And what is the resonant condition we are talking about is that the condition at which the power gets to its maximum value. So the power gets to its maximum value when this impedance value is less. So to make it the lesser, we have to equal XL and XC. So this is the condition for resonance for the series circuit. Similarly, this has to be lesser when or more when this will be zero. So again, to make it zero, these two will be equal, and this is the condition for resonance for parallel circuit. Now we can see is that there are some frequency, current and voltage values that has been compared over here. So first of all, what is the resonance frequency? This is the resonance frequency. This term written over here, omega s. That resonance frequency equal to 1 by root LC. That we are getting from the condition for resonance, that is XL equal to XC, and as you all know that XL equal to omega L and Xc equal to 1 by omega c. So from here we come to this resonance frequency formula. Now similarly for the parallel also, this is the resonance frequency value in terms of inductance and capacitance, 1 by root LC. Now, what is the current for series? As we all know that for the series circuit, we are interested in the current that is flowing through all the elements. That is same for all the elements. So that current value gets to its maximum when we reach to the condition, that is XL equal to XC or resonance condition. I equal to the impedance becomes resistance only. So therefore the current will be maximum. Similarly, here this voltage for the parallel circuit, the voltages are same for all the elements. So therefore the voltage, as the elements are parallel, so voltage that will be maximum when the impedance becomes the higher one, is highest. So this way I can get the VL and VC, that is the voltage across the inductor at the same condition, and voltage across the capacitor at the same condition, where we can see that is the when XL is equal to XC at resonance frequency condition, XL equal to XC, then you see that the magnitude of voltage across the inductor and magnitude of the voltage across the capacitor, they are same but opposite. By this angle we can see. So therefore these VL and VC, they are being eliminated, and the voltage that we will get across means whatever we are supplying over here, that voltage and this voltage will be equal, where these two voltage together will be cancelled out. Similarly, the case is true for the currents for a parallel resonance circuit. Now there is a very important parameter which is called quality factor. Now quality factor, what is the formula? Formula is reactive power it is the ratio of reactive power to the average power. So it signifies that the circuit, the resonance circuit, how much reactive power it is stored in the circuit or in the capacitor inductor to the average power or the real power that is consumed by the resistance. So that is showing the quality factor. So here this curve shown over here, it is having the low quality factor, and this kind of graph, it is showing the high quality factor. Now if we see the formulation of this quality factor for both the series and parallel circuit, so we can see that for let us say for series circuit, the reactive power that is consumed, that is I square XL, whereas the average power or active power consumed, this is the power stored in the inductor, and this is the power consumed by the resistor. And from here, if we, this current for a series circuit, the currents are same, so these currents will be cancelled out, and this XL equal to omega L, by R. So from for series it is omega s represented by omega s. So omega s over here, and here is omega p for parallel circuit. So omega s. Now from here we can write down that omega is equal to 1 by root LC. That is the condition. That is the that we are getting from the condition for resonance for series circuit. That omega equal to both for series and parallel. Omega equal to 1 by root LC. That is the resonance frequency. So 1 by root LC into R. So here from here we get this is 1 by R root over L by C. So this way we get to the quality factor formula for series. Similarly, we get the quality factor formula for parallel, that is R into root over of C by N. So here we can see is that based on the value of the resistance, if we increase the value of resistance, so quality factor will be reduced. Whereas with the ratio of this L by C, the increase of the ratio of this L by C, the quality factor will increase, and that is opposite for the parallel. Now here we will see the impedance, how the impedance, total impedance that is changing with the frequency. So to understand that, we write down the total impedance, that is equal to root over of r square plus xl minus xl whole square. So from the total impedance here, from this we have written that z, that is the mode value, so that we are getting. Now if we draw the characteristics curve with respect to the frequency, then the curve looks like this, where we will see that the at the resonance frequency, the impedance is the minimum one. Impedance is the minimum one. Here you can see that is equal to R, where this XL and XC they are nullified. Uh, and for the parallel, this Z is the maximum one at the resonance frequency. And here, if you is this graph, we can get it um, from the terms, that is resistance, resistance, inductive reactance, and the capacitive reactance. If we individually draw the graph, then it looks like R that changes with frequency. Uh, that is that does not change with frequency, so that is constant. And XL, we know that XL equal to omega L. So with frequency omega equal to pi f, omega equal to pi f. So with the frequency, if we plot it, then it will be this one. And for XC, that is 1 by omega c, 1 by omega c or 2 pi FC. So if we plot it with this frequency, then it will be like this. So now if we add these three and do the if we do the characteristics, or if we draw the characteristics individually, then this will be coming like this. So now if we draw, so as this Z is a complex number, Z is a complex number. Here we have drawn the mod value of it. Or now if we draw the angle, how the angle, phase angle that is changing, then or the power factor angle that is changing, then we can see that at this resonance frequency, the angle that is 0 degree, that means both the voltage and current they are in the same phase. Supply voltage and current they are in the same phase. But when this XL will be greater than XC, that means that is more inductive. So in that case, the angle will be getting increased with the frequency, and that means it is getting more and more inductive with the frequency change. and as it is this frequency that reduces, then this xc becomes greater than xl, and so in this side it is realizing as more and more capacitive in nature. So that is opposite for this parallel circuit that has been plotted over here. Now there is another important term that is called selectivity. So as I have said at the very beginning, is that in for the resonant circuit, what we do, we tune the series or parallel RLC circuit in such a way that that the certain range of frequencies are being selected, at which the value of the current or voltages are the considerable one. So to get the range of the, or to select the range of frequencies at which the voltage or current magnitude are considerable one, we have taken that the root 2 times of the current, sorry, 1 by root 2 times of the current is that value, which is taken that considerable amount. And if we take the power from here, if we calculate the power, then it becomes half of the maximum power. So at this the power consumed is I max square r, that is the maximum power P max. And now if I make that current to 0.707 of I max, then this is the half power frequency. So the square r, so it becomes 1 by 2 times of the P max. So therefore, we can say that this particular point is the half power frequency point. Means the frequencies at which the power uh, gets half of the maximum. Similarly, here also it is mentioned for the for the parallel resonance circuits. Now here to get, here we can see that if we go to the half power frequency values, there are two frequencies. One is F1 and another is F2. So these frequencies are called as band frequencies or corner frequencies. Here to calculate the values of the frequencies, to find out the range of the frequencies at which we are getting the selectivity range. So here we put that ZT, the total impedance formula that I have written earlier. In that ZT, we put this root 2R, and then for this XL, means for these two conditions, we get the F2 and F1, which is final formula is written over here. After some steps, we get to these frequency values. Now here this range of frequencies, whichever is selected, that is called the band width. So this is the width of the band, and here if we do that f2 minus f1, we will get to this value r by 2 pi l. And now from here we can again get this fs and qs formula already that has been discussed earlier. So qs over here, it is 1 by r root over l by c, 1 by r root over l by c. So this one, if we get from this, we can get to this one if we use this formula. Now again, also from similarly from this f1 f2, we can also derive this this formula, where this is the resonance frequency, that is equal to root over of lower corner frequency and higher corner frequency. So till now, as we can see, is that the selectivity that depends on the bandwidth. So here, if we see that the quality factor, bandwidth, all the parameters for resonant circuit, that depends on the values of R, L, and C. So here, I am going to display you that how with the change in the values of R and L and C, how the bandwidth, quality factor, and all these things varies. So here the two graphs over here in the left side, is shown for the series circuit, and two graphs on the right side that is shown for the parallel circuit. And here, as we can see, is with the increase means if we see is that there with the increase in the values of R, with the increase in the values of R, the bandwidth that is getting increased. And also, if we can remember that the quality factor, the formula that is 1 by R root over L by C for the series circuit. So as the increase resistance values increases, the quality factor, quality factor that reduces, and that is opposite for the parallel resonant circuit. So here the statement is written for the series resonance, that is a small QS, therefore is associated with the resonant curve having a large bandwidth. So small QS, that means the larger value of R, that means larger value of R means the bandwidth will be more. So the small QS is due to the larger value of R, and due to that the bandwidth will be more. So bandwidth more means lower selectivity, lower selectivity. While large QS indicates the opposite thing. So larger QS indicates a lower resistance value. Due to lower resistance value, the Q will be larger, and therefore the bandwidth will be less. So we will be having higher selectivity. So this way, for the parallel also we can describe the things. And similarly, here there is another term which is called L by C. So by the increase of this L by C, how the bandwidth that is been changing with the increase of L by C, Q that will be more, and the bandwidth that will be more. So we will get the lower selectivity. So this way, for the parallel, the things are can be explained, or the characteristics can be shown like this. So thank you.